These are bright stars, so you think sent us brighter stars than the ones we attempted on the first night. So last night, we're near the end of the second night. Last night was our first night. This is night 2 of 10 in this sequence. There are many more nights coming up in October, November, and December, another 20. Another 15 maybe coming up in the next 3 months. Anyway, in this sequence of 10 nights, one of the advantages is we have the same instrument. We have DEIMOS, 2 different gratings. In the morning, we tend to use, in the evening, at the beginning of the night, we tend to use the 1200 line grating. Later half of the night, we use the 600 ZD grating because that's what our primary targets need. And grating switches are a bit time consuming and even sort of technologically risky. Things can get stuck.
Oh, okay.
So since the first early primary targets are 1200 line grating, so we are doing the early RLR with that grating, you get more limited wavelength coverage, but you get higher spectral resolution. We're using the narrowest possible slit to get as high a spectral resolution as possible. The more you narrow the slit, the more light spills out because the atmospheric blurring is a certain amount. The more you narrow the slit, the more light you lose, but the higher the spectral resolution. Not the higher the signal to noise, the higher the spectral resolution. We had perfectly good signal to noise. We took, I think, 1 2-minute exposure of each of the RLR. The 13th magnitude is very bright for a 10-meter telescope. And we did this before starting. We had one more such filler target for the beginning of the night, and then we had the main science. But when we did these observations, and I'll try to pull this up in the, depending on what else is going on the spectrograph, I'll try to pull this up. But because we were observing it at a time that's called 12-degree twilight, a little bit before 12-degree twilight, when things are 12-degree twilight in the evening, it means the sun is set. Sunset is considered 0 degrees because the sun is 0 degrees compared to the horizon. 12 means it's 12 degrees below the horizon. And when it's 12 degrees below the horizon, you can still see some residual sunlight in the sky, even though the sun is set. As you know, after sunset, the sky is not pitch dark instantly. Typically, when the sun gets to about 18 degrees below the horizon, it gets dark enough that it doesn't change dramatically after that. So from 0 to 12, it changes very dramatically. 18 to 12, the change is much slower. And 18 to 12 lasts about half an hour here in Hawaii, 25 minutes to be precise. Over those 25 minutes, things get darker. And then beyond 18, there's really very insignificant changes in brightness. There could be changes when the moon rises and things like that, but not due to sunlight, not due to direct sunlight. Well, it's not direct sunlight, but not due to scattered sunlight from the Earth's atmosphere. Scattered off the moon, yes, that happens depending on the moon phase and when it rises and sets. But all this to say, when we observed the 2 RLR, 13th magnitude RLR, in the early part of the night that's about to end now, we got very good signal to noise, beautiful signal to noise. Yale was super happy to see this happening in real time. It was really good for her to see this in real time. And she has late school, so she was up late doing this, and she wants to connect early in the morning because at the end of the night, we'll observe 2 more RLR. Not the same ones because those are now set, 2 different RLR. But all 4 of these RLR that Yuting provided, they're PS1 RLR from Pan-STARRS 1. They're all about 13th magnitude, and we've monitored them before. So whatever spectra we get for them in tonight and the remaining 8 nights will add to the spectroscopic monitoring we've already done with them. Apparently, the 2 we observed in the early part of the night had already been observed with ESI a couple of times, and last year. And the 2 at the end of the night had been observed with DEIMOS and possibly also with ESI. Okay, so when you observe an RLR so bright that you can get a decent spectrum even when the sky is still got some light in it, the advantage of having sunlight in the sky is you can actually see a solar spectrum when you take, all along the slit, because the entire slit is seeing the not completely dark sky, twilight sky. And the reason it's not completely dark is just you're seeing the sun's light reflected off dust particles in the atmosphere, even though the sun is below the horizon, can indirectly send us light. So you see a complete spectrum of the sun. You can see H alpha from the sun, you can see calcium triplet from the sun. It's really beautiful. Now, of course, we know the sun is at zero velocity because the particles that light is bouncing off they're not moving away from us or towards us, so they have no Doppler shift, no net Doppler shift anyway. And you can very clearly see that the RLRA have corresponding emission absorption lines. You can see H alpha, but it's offset from the solar one, and it's offset to shorter wavelengths. We know it's blue shifted, that star happens to be moving towards us. I shouldn't say the star is moving towards us. What is moving towards us, the combination of the star's center of mass velocity and its photospheric velocity. The sum of those two things happens to be negative right now when we observe them. And that's exactly the purpose of that experiment, is to watch the modulation of that. That's why we're measuring multiple times. Now, before we can watch the modulation, one of the important things we have to correct for is part of what we are seeing is the Earth's rotation around the sun. Because the Earth's rotation around the sun could be carrying us towards the star or away from us. And that's different times of the year, because the Earth is moving in a complete circle once a year. So we have to correct for that before we can compare different measurements of the same RLR. Because if they were measured at different times of the year, we have to correct for the fact that the Earth has a different velocity vector pointed towards that object. In other words, imagine a star that's not moving relative to the sun. Not at all. But because of the Earth's motion around the sun at various times, we'll measure a velocity for it, a finite non-zero velocity for it, just by virtue of the Earth's motion towards or away from that object in its orbit around the sun. So that's something that has to be corrected for. Let me start up, fire up the software.
So how does the solar spectrum help us?
Provides a reference. It provides, when you look at a raw spectrum, I don't know what pixel number corresponds to H alpha. I don't know what pixel number corresponds to the calcium triplet. I know the wavelengths of H alpha calcium triplet, but because it's an uncalibrated spectrum, the wavelength calibration hasn't been done. I don't know at what pixel to expect H alpha from the RLR, but because the solar spectrum is so clear, you can see the H alpha absorption line, you can see the atmospheric B band, the A band, calcium, you can see, sun spectrum is something that, is something you learn when you're studying the spectra stars. So you know the main features. So it provides a wavelength reference effectively. A rest frame wavelength reference, because the sun is not has a zero Doppler shift.
And it's basically like a sky spectrum, right?
It's interesting. It's not the standard air glow spectrum. You see a combination. You do see air glow emission lines, even in a 2-minute exposure. You see air glow emission lines, but that's sitting on top of the continuum of the sun and the absorption lines from the sun. So you see continuum, absorption lines, and emission lines. It's a classic. It has everything you ever wanted to know about a spectrum. It has got all of those, all three things going on. Continuum is, of course, from opaque dense gas, the black body part of the sun spectrum. The absorption lines are from cold materials in the relatively cool, or materials from the relatively cool outer layers of the sun. And the emission lines are not from the sun at all, they're from the Earth's atmosphere. But you see all three spectra.
So we have to subtract this off from the RLR spectrum.
Say that again, please.
So we have to subtract this off from the RLR spectrum before we start.
Exactly, you have to do a standard sky subtraction,
Yeah.
But we would have to do that anyway, whether or not the sun's continuum and absorption lines are visible. Just for the air glow, we would have to do sky subtraction. And sky subtraction for these is very similar to the process you've seen before for multi-slit objects. Technically, this is a multi-slit mask that we use for taking the spectrum. They're just slits of different widths that are lined up end on end. We choose the width we want. We chose the narrowest slit width. That's what we observe the RL through. Let me see if I can quickly share the controls of the instrument on the screen, since we are recording this. So let me see. There we go. I'm just firing up the control software. Oh, it won't let me, just a moment. I have my VPN. I have to stop my VPN before I can run this, because Keck uses its own VPN, or yeah, it's dependent on my not running another VPN. There we go. Now it's firing up. And I will share my screen in a moment. I'm keeping you in suspense by giving you a running commentary, but in a moment. Speaking of running commentary, India is playing Australia in a T20 match in just a little bit. And watch that on Shadow the Scientist. Sorry?
Is Evan observing?
Evan is observing. He's actually got a telecon right now. So he is right now, for the next 5 minutes or so, he's got this telecon going. And then, actually, no, his telecon may have ended by now. He said he may be in the midst of observing here. So he may join this, we'll see. Let me share my screen. Roy, I can't, you've been to some of our Shadow the Scientist sessions before, Roy? Is that right?
Oh, this is actually the first time I've made it.
Oh, okay, okay. Couldn't remember. Okay. So we have, this is one of the control screens that is running the spectrograph. Evan is taking, you can see it's taking a 30-minute exposure, 1800 seconds, of which nearly all of that time has elapsed. So 92% done. And in a few minutes, couple of minutes, it'll be done with this exposure. And it's part of a sequence of 3. So you see where down where my cursor is, there's exposure 2 of 3. So it's taking the second of 3 30-minute exposures. 1670, 1680 would mean 2 minutes left to go. Yeah, so while he's doing that, anyway, I'm not interfering with what he's doing because he can switch screens independently of me. So this is a multi-object spectrum, and you can see the continuum of the star there, continuum of the star there, faint continuum right there, very faint continuum here with some kind of mission line, faint continuum there. This is a multi-object spectrum. Then if I go to this window, this shows you how a slit mask is aligned and operates through, and a few others. We were going over this in the earlier STS call. This is the guider camera, where you can see a star that's being used to precisely guide the telescope. These are 2 other stars. The lower part looks bright because it's got a mirror. The upper part is just shiny metal. The lower part is a piece of glass with proper silvering. And this tells you where the telescope is pointed. It says FACSUM, stands for Facilities Summary. So summary of the telescope facilities, where it's pointed, the RA and deck of where it's pointed. This is the elevation angle of the telescope, how far above the horizon. And azimuth is like the rotational angle of the telescope, rotation about a vertical axis. Yeah. And this tells you the position of the top and bottom shutters of the telescope. This is the dome angle. The entire telescope is inside a dome-shaped building that can rotate. The dome part can rotate. So all kinds of information like that. UT is universal time, Greenwich Mean Time. This is the time and date and time there. LST is the right ascension of the star that happens to be directly overhead at any given instant. And it changes at the rate of 1 per second because of the Earth's rotation. constantly different RA stars are overhead because of the Earth's rotation. So LST always changes at 1 per
Exposure
second.
complete.
The reason the telescope is not, RA and DEC are not changing is because it's tracking a star. It's tracking a star. As you can see here, stars are frozen on the detector in this camera. That's why the RA and DEC are not changing. If the telescope was stationary relative to the Earth, RA and DEC, its RA would be changing at 1 second per second, because the telescope with the Earth would be sweeping past different stars because of the Earth's rotation. These are humidity and temperature measures, mostly designed to make sure that it's safe to open the telescope dome. Let's see, we just had someone join the call. Let's see if we can. Where is the window I'm looking for?
CCD readout complete.
Hi, Richard. Richard, I understand that Vicky Newberry reached out to you. And so welcome to our Shadow the Scientist session. Are you connecting from Botswana, or no, your mother's in Botswana. You're connecting from somewhere else from. Where are you connecting from, Richard? Richard, can you hear me okay? I'm gonna see if I can send him a chat. Hey, Richard. Okay, let's see. So these are the different controls again. Screen 1, screen 2, screen 3, screen 4. So it's finished that exposure. Now it's on the third of the 3 exposures.
By the way, does Keck use an artificial guide star, or just, natural stuff?
You can do both, but it's not using either right now because we're not using adaptive optics right now. So adaptive optics isn't used all the time. It's used only for on specific nights for specific science projects. So that's when, so the guide star I was talking about, these are, of course, natural guide stars, but these are not being used to correct the correct for the twinkling of the stars by the Earth's atmosphere. Is that the kind of guide star you were talking about, or just for pointing the?
Yeah.
So those are only used on when we're using an adaptive optics system, and DEIMOS is not located behind an adaptive optics system. In fact, it has such a large field of view that it's impossible to correct such a large field of view at once, because different parts of the DEIMOS field of view are looking through different patches of the atmosphere, and that's super difficult to correct. Adaptive optics, using adaptive optics. Adaptive optics usually does good correction over a very small patch of sky, less than an arc minute. And DEIMOS is 16 arc minutes. So we use other instruments with adaptive optics. We use a camera called NERC2, near infrared camera 2 on Keck, which is a small field of view, very fine pixels.
It's mostly for imaging, right?
Can be used for imaging or spectroscopy. If you're working in a very crowded field, or you have 2 objects that are very closely separated and you want one, not the other, then you would use adaptive optics to sharpen the image and then put the light into a slit. So there's a spectrograph called NIRSPEC, NIRSPEC. Same name as one of the instruments on James Webb, but this is the Keck version of NIRSPEC. And that can work behind an adaptive optics system. So So you first correct with the adaptive optics system, and then that light goes into an imager or a spectrograph. So last year around this time, we were using, or in August last year, we used adaptive optics to take some images of star clusters in Andromeda. And there we were taking images using NERC 2. Richard can't hear us. Richard, are you able to hear us now? Ask him again. So Richard is going to disconnect and reconnect. So let's hope.
Also, you mentioned something about using the 1200G grating early in the night.
Using what grating? Sorry.
The 1200G grating, I think.
Yes.
Yeah. Can you tell me a bit more about that?
No, so the main science program that's going on tonight is spectroscopy of stars and dwarf galaxies, but they don't all have the same goal. Some are trying to measure velocities, some are trying to measure chemical composition. For chemical composition, it's helpful to get spectra in the blue part of the spectrum and red, so wide wavelength coverage. Whereas for the velocity measurements, we want the highest possible spectral resolution. So for the targets for which we care about velocities, we're using the 1200G grating. And for targets for which we care about measuring chemical abundance, we're using the 600 line grating. They're switching between gratings can be a little tricky, and one of the grating holders is a bit fussy. This is an old instrument, and in fact, earlier tonight when we were trying to make our switch from 1200 to 600, we lost a little bit of time because it didn't successfully switch from one grating to the other. It was sort of stuck between gratings, so we had to do some things to get it unstuck. Because of this, we're trying to avoid frequent grating changes during the night. So since we know the early targets are going to be using 1200G grating first half of the night, the RLR we observed at the beginning of the night, we used 1200G. And then middle of the night, we switch from we've done with all our 1200G targets, we go to the 600ZD targets. So at the end of the night, when we observe an RLR, we use the 600ZD. That's what I was.
Any particular reason why we observe the 1200G targets first?
It just so happens that those are the objects that have a lower RA and they're up earlier in the night. I think I see. Richard has reconnected. Richard, can you hear us now? Can you hear me now? Richard, please, if you can hear us, or let us know if you can hear us now by typing into the chat, please. There we go. I saw it said connecting to audio, but you're muted right now, Richard. Are you able to hear me now? Okay. Just want to check on something very quickly. Stop my screen share for a moment. Let's see. Now the recording is still going, that's no problem, but okay, thank you, Richard. Okay. As long as you can hear us, if you have any questions, feel free to ask us. You know, we're trying to take spectra of stars in some of the satellite galaxies of Andromeda, and then later we'll be getting some spectra of a class of stars called Aralari. But I might ask Richard by chat. Oh, this connection is bad. Roy, are you bracing for the start of the new term? Starts in a couple of days, right?
Excited, yeah. 2 days now? Yeah.
Yes.
Too much time off, I get bored.
This is your, will this be your last academic year at Santa Cruz?
Theoretically.
Okay.
Unless I get accepted to grad school at Santa Cruz.
Okay.
But we'll see.
Are you, you're applying to grad school at Santa Cruz and other places, or only to Santa Cruz?
So I just asked the first questions about this yesterday. I was on the,
Okay.
I was on the call with Brandon Day, and he just
Oh,
gave me.
good. Okay.
So if everything goes the best that it possibly could for me, then yeah, next year I'll be starting grad school somewhere.
Would it be in physics or astro?
Astro.
Okay.
If not, yeah. This is the direction I'm leaning anyway. I guess we'll see how it goes.
You know, and some departments have combined physics and astronomy departments. That's not uncommon, actually quite
Okay.
common. Our department is sort of unusual in having separate departments. Again, that's not completely unheard of. Some of the bigger astronomy departments tend to be separate from their corresponding physics departments.
Sure.
Do you know whether you'll apply within the US or outside as well?
I hadn't really considered applying abroad.
Okay.
And yeah, I suppose I'd probably go anywhere in the US.
Okay.
Yeah. Again, I'm starting this process.
You're
maybe,
just starting this.
but really, yeah, just not
I'm
really.
happy to chat with you about it because this is something I've been involved in at UCSC for a while from the other side, from the admissions standpoint, PhD admissions, for just specifically for our department, because PhD admissions are done separately, department by department. There isn't a central admissions office like there is for undergraduate.
Okay. Well, it seems like you're a good friend to have then.
I'm a good friend to have, but no, nothing else. It's just, you know, I've seen what admissions committees need to look for and what questions they ask, etc. So it's not a big secret. It's pretty, you know, clear what people look for, and it's not exactly the same from university to university, but it's not that drastically different either. But
What would a competitive student look like at Santa Cruz at the Astro department?
You.
Well, done. Pleasure doing business with you.
Yeah. So, you know, they're generally a few things. You know, they're looking at, I would say, two things, but looking for looking for promise in two areas. And how they look for that is through different pieces of different parts of the application. It's not like there's an exam for each of those two parts. The two parts are looking at a solid foundation in physics, because we're in astronomy astrophysics department, and there's a lot of physics applied to almost every project, every research project, every class you take in astrophysics. You see that in your undergraduate classes. There's a lot of physics, some amount of statistics and math and chemistry even. But they're looking for a strong foundation in physics. And when I say physics, I mean the mathematical parts of physics, the more intuitive parts of physics, the quantum mechanics, chemistry, the standard but broad physics foundation. And how do you look for that in an application? Well, there's the transcript. And now that we've had the great Grexit, no GRE, it's, it was never a very good measure of physics foundation. It was
Is that officially gone now? Just at Santa Cruz, or is that
many places.
okay?
And it's at mostly astronomy departments have gotten further away from it than physics departments. One of the things, when I say it's gone, it means different things at different places. Santa Cruz doesn't allow students to submit a GRE. They will not accept it, right? They will not accept it. Because the submission process doesn't happen. I mean, the self-reported scores, we've gotten rid of that question. There used to be self-reported scores plus reported by ETS, Education Testing Service. We've gotten rid of those things. We don't. Some places don't require it, but they will accept it. And some people require it. Some people don't require it, but will recommend it. Some people require it. So there's at least these 4 flavors of things that we're in the complete Brexit category.
Okay.
Which is ironic for me because I would not have gotten into grad school if the GRE were not a factor. Clearly, because I applied as a foreign student and there was nothing else in my application that could have been positive. Absolutely nothing. So now, without the GRE, it's looking at college transcripts, but not just looking at the overall not just looking at the overall GPA, but rather looking at what classes
by the
the
way,
student. Yeah, sorry,
I have shared a link in the chat, Roy. You might want to check it out. It's like a list of places that don't ask for GRE.
Nice. All the places I'll be applying. Thank you very
Angelina,
much.
Angelina, do you have a moment to introduce yourself? Where are you connecting from? Angelina, could you hear me? You're wondering.
Yes.
Yeah, go ahead, please. Where are you connecting from?
I'm connecting from Faridabad, Haryana.
Oh, wonderful, wonderful. Okay. How did you find out about Chara the Scientist?
My mother had received email about it, so I thought to just take an interest and just to see what is happening.
Do you know how she found out from which organization? I'm curious because we are trying to reach.
I don't know.
No problem at all. Are you a student in school or college or?
I study in a school.
Okay. Thank you for connecting. Faridabad is near Delhi, right? It's not far from Delhi. Okay. So Roy, I was so the way our admissions committee, and I'm not on the committee this year, I wasn't on the committee last year, but I served on the committee or chaired it for about 20 years. And over those times, I saw quite a bit of change, for example, in how the GRE was used or not used, many other kinds of change, how different parts of the application were reviewed. Let me, so what, I'm going to share my screen so that while we're talking, so.
Okay.
Yeah, so you're seeing the controls of the telescope you're using, Angelina, and in a few minutes I'll explain what we're looking at here. So Roy, what happens is people look at what classes the student has taken in college, typically not before, but in college, and that includes community college and college, looking at what classes the student has taken, how they've done in those classes. There's a sense of, how, try to get a sense of how rigorous the class is and how the student has done in those rigorous classes.
Okay.
Now, and Angelina, what we're talking about is sort of the college admission, the PhD admissions process at in our department. So the other way in which the committee can gain insight into a student's physics background is through letters of recommendation. Sometimes you're getting a letter from someone who's taught. The applicant is getting a letter from a professor who's taught them in a class in which they've done well. In that case, the professor can talk about, the applicant's strengths in certain areas, physics or mathematics. So a third way in which you gain insight into an applicant's foundation in physics is how they're writing about their physics or their research, and you get a sense of what how technical that is, how deep their understanding might be. So that's a little tricky. You don't want to write in such technical terms that if you're, if the committee folks are not experts in that area, then you may lose them. So it's a balance. The second thing that committees look for is excellence in research and having some research experience, which Manjuma, Aparajito, Roy, you all have research experience working with me. So research experience comes through the student's essay, through their CV. If the student writes about what research projects they've done and on their CV, sometimes students have published papers. They'll list those on their CV.
Is this just a normal CV, or is it like for your academic career?
It's typically academic career. It's academic focused. People maintain different versions of their CVs depending on how they're using it, but this is sort of a more academically oriented CV. There's also sort of form questions that they ask that are sort of CV related in addition to the CV itself. I'm just noticing one thing on the, so those are the main things that are used now. One of the things I'm looking at here in this 2D spectrum, I don't know, can you guys see my cursor?
Yes.
That I'm moving around here. Okay. Do you see these two blobs here? You see
Yes.
Yeah, these are produced by a galaxy. So we wanted to target stars in a satellite of Andromeda, but when you see emission lines like that, these are emission lines. They're a background galaxy. That means it's a background galaxy. It's not a star in Andromeda.
Okay.
Now, let me see. I don't know. I don't want to, right now, I'm in view only mode. If I open this, you'll see I'm in view only mode. I don't want to interfere with Evan's use of the cursor. If I were, so I'm going to wait for him to give me the green light before I switch from view only to interactive mode. What I was going to do is pan around a little bit to see if there are other emission lines in addition to these two, in an attempt to identify what those emission lines are. Right now, just looking at those two, I can't tell you what they are. But once I see more of a pattern, I might be able to tell you. So you can see there are 8 CCD detectors in DEIMOS, 4 at the bottom, 1, 2, 3, 4, 5, 6, 7, 8. By the way, you can see CCD5 is working beautifully now. This was not a problem for the RLR spectra that you were using, Roy, because those don't use CCD5. But for multi-object spectra like these, all 8 CCDs get used, and CCD5 had an elevated noise level and so wasn't very helpful. It had started to have problems in 2018, and after some repair work in 2022, it's functioning fine. Fingers crossed that it continues to work fine.
Okay.
they don't completely understand what exactly which part of they made a bunch of changes in an attempt to repair this, and they think the new ion pumps really help with this. The electrodes were getting all gunky with new material because it wasn't maintaining a perfect vacuum. These ion pumps are meant to be replaced every 5 years, and DEIMOS was commissioned 20 years ago, and the original ion pumps were just replaced.
Oh, okay.
How replaceable are these CCDs?
Very difficult to replace because
Can't just take apart an
inside-
iPhone.
You could, but these are very special purpose CCDs. And what is tricky about them is you notice there's 8 of them, and they have to be perfectly planar. Otherwise, one would be out of focus, one in focus. And so to a level of about a micron or so, they have to be mounted in exactly the same plane. And it's all 3 axes. It's multiple degrees of freedom, right? If you have 2 CCDs, you can imagine they could be at slightly different levels. So there's piston. You don't want them to be rotated. You want the rows and columns to be running exactly parallel. There's translations also because you want the tops of the CCDs to be aligned. It's a very precise operation.
Right.
Not to mention, it's best if you don't want to replace only one of the CCDs. You want to replace all 8 because you want them to have similar characteristics. So DEIMOS is going to go through major brain surgery. In fact, Evan is leading that effort to replace all the CCDs so that the lower CCDs are more blue sensitive. The upper CCDs are red sensitive. Right now, they're all identical CCDs. So it can be optimized, sensitivity
Oh.
improved.
Really? I thought the red side is thicker or something.
Red side is what, sorry?
Yeah, I thought the red side is thicker or something, to pick up longer.
Yeah,
waves.
so generally, you want thicker CCDs on the red side. Are the current CCDs different between red and blue? I don't know. Didn't think there were. I thought they were using thick CCDs for the whole thing, but maybe not. All 8 CCDs, but I may be wrong.
I don't see any significant difference between the cosmic ray hits on the 2 sides.
That's one way of knowing. Yeah, but usually in the DEIMOS in the DEIMOS instrument pages, it will say. I'll check with Evan when we connect in a few minutes. Are all 8 CCDs? Do they have identical characteristics? I'm not sure. You would know for certain. I think the new ones.
We have a question in the chat.
Yeah.
What are CCDs?
Let me see. What are CCDs, Pradipto? Okay, so a CCD stands for charge coupled device. I'm going to type this in. This is what your smartphone uses when you take a picture. This is in very common use, these CCDs. So they're typically pieces of silicon, flat substrate of silicon, on which certain other materials are applied, and to create potential barriers, electrical potential barriers. So as you know, silicon is a semiconductor. So what happens is, because of this is called doping, where you put different material, not the doping that gets you in trouble in the Olympics, not that kind of doping. So you put a different material, you put a thin stripe, another thin stripe. This
like the P doping and N doping.
Yeah, exactly. So you create a set of rows and columns that way, and you create pixels that are, you have these CCDs are rectangular. They're 2,000 pixels across an X, 4,000 in Y. So 2K by 4K CCDs, 2048 times 4096. These are powers of 2. Now, sure, I can do that. So these CCDs that run from, these 2K by 4K CCDs, 8 of them, the way they work is you can think of a charge coupled device as an array of buckets, light buckets. They're of course silicon, semiconductor, but because of the the doping along the rows and columns, each element of the silicon, also called a pixel, is like a light bucket. It can collect light. By the way, the word pixel is a made-up word. It stands for picture element. It's one element of the picture. Okay, so what happens is if you think of pixels in a charge couple, so this is called a charge coupled device. So if you think of the pixels in a charge coupled device, you can think of them as an array of buckets, each with a square cross section, that are arranged in a perfect grid. Okay? And instead of pixels, if you imagine buckets, and instead of light raining down on a CCD, imagine it's raining. Imagine it's raining outside and you've got this array of buckets. That's literally what's happening in a CCD. It's raining light, and you want to know how much light is hitting this pixel versus that pixel. So every pixel, its job is to take the electrons that are released by the photoelectric effect of a photon striking silicon. That electron that's released by the
Exposure
photon
complete.
gets trapped in the pixel, doesn't get to travel to a neighboring pixel, unless there's so much light that hits a pixel that the bucket overflows and light starts spilling over into neighboring pixels. You can see that when you have a very bright star. Anyway, you do this when you open the telescope up, and when it's taking an exposure. That's what you're doing. You're allowing light to hit different pixels. After that's done, when it says it's reading out the silicon detector, what it does is, in turn, it empties all these buckets of charge, just like you would empty buckets of water to measure how much water each one had collected. You empty all these buckets of charge, see how many electrons or how many photons were trapped by each pixel. You do this row by row, and you do this for all the rows, and then
CCD
that
readout
process
complete.
takes something like 40 seconds for the 8K by 8K DEIMOS detector. You don't read them all out with the same one amplifier. Each CCD gets read out by a separate amplifier, separate. Each one has its rows and columns dumped separately. Yeah, it is important to use silicon for these. I mean, there are other materials used for devices like this. For example, there's something called a mercad telluride device that's used for infrared astronomy. Mercury, cadmium, tellurium, mercad telluride, HgCdTe. There are detectors that are made of indium and antimony. InSp detectors, IN-SB. IN is the symbol of indium, and antimony is SB, capital S, lowercase b. So there are different flavors of detectors. What you're seeing here in the optical is very commonly used as silicon detectors.
Exposure complete.
This exposure complete is happening in this window over here.
So CCDs are kind of like the optical sensors of a telescope. Like in camera, we have some sensors that capture light. So in telescope, the CCDs are the one that captures light.
Yeah, it's exactly the same actually. If you have a digital
CCD
SLR
readout
camera,
complete.
it's using a CCD.
So how are they different from the one that I have in my camera?
Identical.
I think-
Identical.
I think
Well, it's not identical.
yeah,
Sorry.
I mean, because the modern cameras mostly now use CMOS detectors, not CCDs.
That's true. There
yeah.
are some practical differences between, when you take a picture with your digital SLR, you get a color image. That's not how CCDs work. CCDs, you have to put a filter, take an image in one color, then take another image in another color. So the way these digital camera devices work is some pixels are green sensitive, some pixels are red sensitive, some pixels are blue sensitive, and they're sort of scattered throughout the body of the detector. And so it interpolates among them to create the red image, blue image, green image every time you take an image, and that's how it creates a color image. That's not how CCDs work at all. All pixels have the same, or we attempt to make them the same sensitivity. They're not identical, but we try to give them the same sensitivity. And the way you control light, the color of the light, is you put in filters in front of the camera. You put in a blue filter, you measure the intensity of the star or galaxy in blue light, and you change the glass filter and take on. So you don't do the color selection using pixels on the detector. You use it using typically glass filters. It's like the glass filter is very much like a stained glass in a church. When you look through a particular colored
Exposure
glass, it's
complete.
letting in light of that color. If you look at a sun through a blue panel of stained glass in a church, the sun looks blue just because it's only admitting blue light. So that's how filters work. And that's how astronomical cameras discriminate between light of different wavelength. And this is a very
CCD
important
readout
difference between how
complete.
digital cameras and astronomical cameras, between sort of personal use DSLR cameras work and professional astronomy cameras.
And CCDs do have some advantage over, the CMOS detectors, I think. Mostly bigger CCDs are more linear in their response.
That's right. They're also more sensitive to low light.
Yeah, that's right.
One of the really cool things about, I have a friend who works on image processing as a profession. And you know that every camera, my Nikon, I don't have a Nikon. If I did, if I had a digital camera and you had a different digital camera, each of them have a slightly different detector characteristics. There's some pattern of pixels that have lower sensitivity than others, etc. That's different from one make of the camera to the other, because this doping process is not can't be perfectly replicated from one to the other.
Yeah, it seems like how two processors can be of the same make, but they must have some very minute differences.
Minute differences, right? So this friend of mine works in an area where if you give him a series of images, he can tell you whether it came from a particular camera or not. And the way they do this is they look for, you can imagine that's very, very helpful in the security business. So they can, you imagine if you take a bunch of images and you just average them together, what you're going to get is like a white light image, because there's light when every pixel picked up light and sound. If you have enough of these images, you should get a perfectly smooth white light image, except you see dips and bumps depending on which pixels are more sensitive than the others. So if you have enough images, you can tell exactly what the detector pattern of sensitivity was, and that's the signature of every specific detector.
Literally like a fingerprint.
Like a fingerprint, exactly. I'm just going to quickly pop my head into the next room to see what, if Evan's able to join this call so he can walk us through what he's doing here. So I know he's, one thing we can tell is by using this facility summary that he's looking at A22BL2. A is Andromeda, 22 is the satellite number 22 orbiting Andromeda, B for bright stars, L because it's late in the night. He has a different target for earlier in the night because that determines, things like parallactic angles, etc. And 2 must be the second of the late masks. So that's what he's on. And if I look at this window, it'll tell me how many seconds left to go. Yeah, this says that it's the better part of 30 minutes left to go. And if I look at this window down here, it's just started the first of 3 half-hour exposures. So we have an hour and a half to go before this is, before observations of this galaxy are finished. That will take us, sort of been going for about a minute and a bit. So it's 7 for you, it's 4 for me. That means it'll go until about 5:30, little after 5:30. Oh, I see Evan has just cut the exposure time from 1800 to 1620. because 5:30 would take it too far into twilight. So one thing we can sit here and do is figure out when this sequence will be completed, because you can see it's about 2 minutes in. So at 7:09:30 Pacific time, it's 2 minutes into the exposure. Let me calculate. So 2 minutes, 1500. I'm going to do a little calculation, sorry. 25. So it's got 25 minutes to go on this exposure, plus next two exposures are 27 minutes. 25 plus 27 plus 27. Wow, at this time of night after staying up, I can't do this in my head, can I? It's 79 minutes, right? 27 plus 27 plus 25, 79 minutes. Add that to 7:09:30. 7:09:30 plus, I think that takes us to 7:28:30, if I'm not mistaken. Right, you guys do this calculation. What time is this exposure sequence going to end?
It's 1500 seconds. 25 minutes. Why does
Sorry?
it say 1620?
Yeah.
Is that the total time?
Yeah, that's the total amount of time. Out of that, 212 or 213 has elapsed for the first exposure. The next two exposures will be 1620s. So I'm calculating 7:28:30 California time. Right now, California is 7:11:60.
That's 25 minutes. Yeah, so 20 minutes, 28, and 25 more minutes. So 7:30, around 7:30.
7:28.5 is what I'm calculating. Yeah,
Yeah.
7:30 it will take us to. 7:30 sorry, 8:30. 8:30.
Yeah, right.
30, which is 5:30 here in Hawaii, which is a little bit after 12-degree twilight. Let's look at this graph here. So today is the 20th, and 12-degree twilight is at 5:23, or California 8:23. So it'll be 7 minutes after 12-degree twilight. I'll have to check with Evan to see if that's what he intends, or
Did you get any sleep tonight?
sorry,
Did you get any sleep tonight?
a little bit, yes. Between the two STS sessions, I took a nap. Sleep after this session. I have a meeting at 1 o'clock California time, which is 10 a.m. So get about a little less than 4 hours of sleep. It's challenging to be observing because you're trying to take daytime meetings and do this nighttime work. So it is, while I enjoy this very much, and observing with telescopes is the most exciting part of my work, it's still challenging. If I didn't have to do all my daytime work, that would be fun. Observing on weekends is much better than observing on weekdays. You guys have been asking very good questions. If there's other questions you have about anything you're seeing here, please feel free to ask. Next thing here is a flexure compensation system. Let's see what's going on with the other windows. This is a mask alignment image. This is what Evan took before the first of the 3 spectral exposures. That's why you're not seeing a spectral exposure here. The last thing it displays is the alignment image. And this is also from alignment. You can see these peaks are perfectly centered on the pedestal they sit on. And this is telling us a little bit about the image quality. It's quite good. Actually, 0.8. It's quite good. What is this? The mask alignment tool have? Oops, not that one. This one. 0.9, 0.8, 0.87. That's something called seeing, which is a measure of how blurred or not the atmosphere is making stars, how much twinkling is going on.
Would this number trigger you to want to use the adaptive optics, or would you just know ahead of time based on the target you're observing?
You don't know ahead of time because you can't predict the atmospheric conditions so well. Although part of the forecast at observatories tells you not just about cloud cover and rain and snow and things like that, but they also tell you how turbulent or not the air will be. They actually make predictions of what the seeing will be. This quantity is called seeing, just like SEEING. It's a measure of the degree of blurring. And it's measured as a full width at half maximum, measured in arc seconds. Things below 1 are generally good, and this is coming in at 0.87, 0.9. It's at Keck we're spoiled. The median seeing at Keck is 0.8 arc seconds, so this is actually slightly worse than typical. Last night, there were periods, or even tonight, we had periods of 0.6 arc second seeing. Last night started with 0.5. So sharper the less turbulence there is, the sharper the image of the star, the better the quality of the data, whether you're taking spectra or images. This is what sets James Webb apart, because by being in space, it doesn't experience atmospheric turbulence. Same for Hubble. It takes very sharp images. Is able to see very faint stars.
Could we think of this as like an uncertainty in each pixel? The seeing.
Let me think about that. The way seeing is characterized is by something called a point spread function. A point spread function, in general, is a 2-dimensional function that says if you have a single point of light, what's actually a single point of light in the universe, it maps into a 2D function. Typically something that resembles a 2D Gaussian, that it's something that's a Gaussian along any, if you take any cut across this blob of light, it looks like a Gaussian shape. So it can be represented as a product of a Gaussian in X and a Gaussian in Y, for example, with exactly the same. If it's not tilted or elongated or anything like that, then if it's perfectly round, then the full width half maximum in X and the full width half maximum in Y are identical. Or in fact, full width half maximum on any axis is the same if it's a truly circular Gaussian, 2D Gaussian. So a point spread function is a measure of a mapping of a point onto an actual image. And the reason a point doesn't map onto a perfect point is partly because of the blurring of light by the Earth's atmosphere, twinkle, twinkle, little star, is what's going on there. But even if there was no atmosphere, which, Hubble and James Webb have no Earth's atmosphere between them and the stars, because of the effects of diffraction, because the mirror has a finite size, you get some amount of blurring anyway. And they're the big
quantum effects.
Just from wave effects, exactly. So the way that works is the bigger the mirror, the sharper the image. So having a bigger mirror Webb versus Hubble. Hubble is 2.5 meters, Webb is 6.5 meters. A bigger mirror does two things: sharper images, but also collects more light per unit time, and so is able to make more sensitive measurements. Fainter stars, etc., fainter galaxies. Of course, bigger is also more expensive to build, but that's what you get for that. That's what you get for that extra expense. Those two gains.
They're building that new cool telescope in South America. I don't want to call it the VLT, but it's one that it's like a new type of adaptive optics where they're actually deforming the mirror in order to compensate for this atmospheric effect.
Right.
Is
so
there?
Yeah, deformable mirror is standard for adaptive optics. That's what happens at Keck and VLT. So VLT is quite old, actually. It's EELT, that's the new telescope, European Extremely Large Telescope. It's also being built in Chile.
Okay.
European, these class of telescopes are called ELTs,
Mhm.
Extremely Large Telescopes. So it's very unimaginative name. But the European ELT, there's an ELT called the Giant Magellan Telescope that's being built by Carnegie and a consortium of institutions. And then there's the 30-meter telescope that Caltech and UC are, some other institutions are doing together. Canada's involved in that. India and China involved in TMT.
Do you think by increasing the aperture of Earth-based telescopes, we can make up for the fact that we're stuck on Earth? If we can, James Webb is a large telescope, but we're building much, much larger ones based on Earth. Is it possible that our technology is going to be able to compensate for the atmospheric effects enough to make up for not being in space?
Let me see if I can answer that question. The atmosphere does different things, more than one thing. So you can compensate for certain things easily. Impossible to compensate for certain other things. For example, the atmosphere absorbs light at certain wavelengths. And
Yeah, those
once that
photons.
light is gone, it's gone. Right?
Yeah.
So the way you compensate for that is by sending the telescope above the Earth's atmosphere. So there's no substitute for sending. So for example, certain kinds of astronomy can't be done from the ground.
No.
Ultraviolet astronomy, many flavors of IR astronomy, not all flavors, but many flavors of IR astronomy, gamma ray, X-ray astronomy, these have to be done from space. So that's one of the effects of the Earth's atmosphere. It blocks light of certain wavelengths. Now, the twinkling of starlight and the blurring that way, that can be accounted for by adaptive optics, but it's not a perfect correction. You correct some fraction of the light. It's something called the Strel ratio. You might correct only 10% of the light. The remaining 90% spills into this. It's spread out as much as it would be without adaptive optics. 10% is, it's not, depending on what wavelength you're working at and how fancy your DM system is, you could get, 50, 60% Strel. Strel is STREHL. It tells you what fraction of the light from a point source has been effectively corrected into a diffraction limited core, while the rest of it still forms the wings. But Strels of 100% are difficult to achieve. 80, 90 maybe, but 100 is difficult. So there's some, loss of sharpness from that. But technically, the adaptive optics, the sharpness of an image of that core, of the diffraction limited core, depends on lambda divided by d, wavelength divided by diameter of the telescope. In that sense, ground-based always wins because you've got a bigger telescope, on the ground always than you do in space at any given wavelength. But you're not correcting all of the light, and you can only do so certain wavelengths, not at others. Easier to do in the infrared than in optical. So it's a complicated question.
Sure. Yeah, so considering that the absorption of the atmosphere, some of the light that you want to look at is just not ever going to get to the Earth. You got to go, yeah. That makes sense.
That's what keeps us alive, right? I mean, if all the UV rays and X-rays and gamma rays were getting through, they would cause dangerous mutations. Already they do, right? Because of the ozone hole, and people put on SPF. These are, people put on sunscreen because UV rays are harmful. Basically, the more energetic a photon, the more likely it is to break molecular chemical bonds. And, of course, those molecules are critical to us, DNA, and can't afford those things to break. And we can't afford to have those things break. But that very fast. So it's interesting connections to human life and survivability and our genetics and all of that. One of the really cool things that I talk about this in my class. Absolutely, I'm absolutely fascinated by this. If you look at the Earth's atmosphere, you can make a graph of wavelength on one axis and how transparent the Earth's atmosphere is to that wavelength, how opaque or transparent it is. Okay? Imagine you make it how opaque it is. So the Earth's atmosphere is very, very opaque at most wavelengths, except for a small sliver of what we call visible light. Violet, indigo, blue, green, yellow, orange, red, then it becomes sort of opaque again. There's another opening in the radio part of the spectrum. So for a species to develop on Earth and be able to rely on vision, we either had to depend on radio waves for our eyes or visible light for our eyes. Our species and most species on Earth evolved to use that tiny sliver of the spectrum that the Earth's atmosphere lets, and that can't be a coincidence. This is natural selection, right? So if you had creatures on Earth that were whose eyes were sensitive to other wavelengths, infrared, gamma rays, X-rays, they couldn't rely on sight as effectively as creatures that are using violet, indigo, blue, green, yellow, orange, red. And I find that a beautiful connection between Darwinian selection, how our eyes work, and the detailed properties of our atmosphere. Now, why don't we have radio wave capable eyes, radio sensitive eyes? Because radio waves are so large that our eyes would have to be very large. Radio dishes have to be very large, otherwise diffraction is not able to, because of diffraction, not able to capture such things. You can imagine on another planet somewhere else, even if it had exactly the same atmosphere as the Earth, maybe life could have evolved in a way that there were radio sensitive things only and not. It's a fascinating interplay in biology and physics. Biology of natural selection, survivability and all that, and reliance on sight for survival. Rely on sight to escape our predators, those sorts of things. And versus the mundane, versus the details of the chemistry of the atmosphere, what elements cause what absorption lines, what wavelengths to be absorbed, what wavelengths to be transmitted. It has serious implications for searches for life, right? Because our atmosphere has certain properties. Other atmospheres will have different properties. And it has serious implications for how you look for, what you look for when you're looking for life. A pioneer in the search for extraterrestrial intelligence died recently, and his name is Frank Drake. Frank Drake of the Drake equation passed away, I think it was 2 weeks ago. He was a Santa Cruz professor. He was a dean of physical sciences at Santa Cruz, and then he retired and started the SETI Institute for Extraterrestrial Intelligence. And when Frank retired, UCSC hired 2 professors. I was one of them. So I'd gotten to know him for years. I used to run into him in Mountain View. SETI Institute is not far from my home. I last ran into him at a Chinese restaurant. And it was funny, I was sitting at a table with my family, and I looked over in the next table, there was somebody wearing a t-shirt, and the back of that t-shirt had the Drake equation on it. And I found it curious, and then I found that Frank was sitting next to that person. These are all people from the SETI Institute who were, one of them happened to be wearing the Drake equation on their t-shirt. So The Drake equation, if you don't know, is the famous equation about calculating the number of, it's a way of quantifying our ignorance about the number of living things in the galaxy, number of living intelligent civilizations in the galaxy. Frank Drake is the name. I'm going to put that name in the chat. And he was the pioneer for something like SETI, Search for Extraterrestrial Intelligence. This exposure has about less than 5 minutes to go.
Looks like Frank Drake was in the Navy,
Is that right? I didn't know that.
an electronics officer. The USS Albany.
USS what, sorry?
Albany.
Albany, okay.
Heavy cruiser Albany, not the submarine.
Okay. And Roy, you served in the Navy, right?
Oh, yes. 5 years in submarines.
Wow. Which years were they? Are you allowed to talk about it? I'm not sure.
Oh, yeah. I can't tell you where we were on the map at every given moment, but other than that, 2010 to 2015.
I see.
And 2010 was all boot camp and school training.
I see.
So yeah, 4 years actually on board the USS Montpelier out of Norfolk, Virginia.
Oh, wow. Okay. What fraction of the time did you spend of those 4 years? Would you say you spent in a submarine at depth versus, say, at sea level or on land?
Maybe a quarter.
Wow.
Because we're lucky, we crashed our boat, and so we missed the deployment and deployment workups. It's not unreasonable to have a year where you're gone for 80% of the time. Yeah, and when you're submerged as soon as you get 12 miles out.
You see, and so in terms of circadian rhythm, day-night cycles, you must have to pay sort of, that has to be deliberately, like, how do you cycle light and, how do you cycle, how do you simulate day-night?
So it gets kind of weird. They have red lights on the boat. So theoretically, the lamps they choose have a broad spectrum, so it's supposed to help. And then we have red lights. And so in like common areas or hallways, like the dining facility, the lights will go red when the local sun is down.
I see.
But we shift to Zulu time as soon as we submerge. So we're on GMT no matter what.
Yeah.
And on top of that, things may have changed. They were trying to move away from it before. I don't know if it will. We run on an 18-hour day.
Wow.
So yeah, the 24, it's just the way that the watch standing responsibilities worked out, but we'll have 6 hours sitting at the controls doing whatever, 6 hours to do extra work or hang out, and then 6 hours to sleep.
Wow.
Mhm.
That's worse than my schedule.
Yeah, well, yeah, I would rather not have to go back to it.
Wow.
You get used to it quickly, though, a couple days. But the circadian rhythm just kind of goes out the window.
See. Oh. Did you study on the East Coast to prepare for the Navy? I thought they were kind of, is West Point something?
There is the Navy Academy is out in Annapolis, Maryland.
In Annapolis, okay. Then I know there's a Naval Postgraduate School in Monterey.
That's true. That's true. And I'm actually not very clear on what they do there. It's not some secret thing. It's just I don't know.
No, I know. One of my friends used to
Exposure
teach there.
complete.
So I think it's I think he taught computer science there.
Mhm.
And is West Point mostly for other parts of the military and not for the Navy?
West Point is the Army Academy,
Is the Army Academy? I see. So there's no Air Force presence or Navy presence there.
not at those schools. There is an Air Force Academy and a Coast Guard Academy.
I see.
They're, I guess, a less storied tradition.
A couple of my former students are at one studied at West Point for undergraduate. One teaches there.
Yeah, that's a prestigious place to be.
It's upstate. Well, not very far upstate New York. It's on the Hudson, right?
I believe so. I'm not even sure. Spent more time in Annapolis.
I
Never
think
actually
it's-
visited the school though.
I see.
I had a
think
few
it's-
officers on board from Annapolis, and
CCD readout complete.
Got it.
less than half had gone to the academy, and the other half had just gone through ROTC, or you just went to college and then joined the Navy, or however else they did it.
Got it.
I didn't notice a distinct difference between the two groups. Some of them were cool, some of them weren't.
For any group of people, I suppose.
Yeah. Learned some cool science though. Learned about electrolysis, learned a little bit about nuclear power, some about radiation.
Aren't you well protected from radiation there? Or because these are,
We just had to learn about it. We had to wear dosimeters.
I see,
Mhm.
because of what the submarines are carrying, presumably.
Well, it's nuclear powered.
Yeah, that's what I mean. Yeah.
Yeah, so all of them are now.
Okay.
But it's not dangerous. There's never
I
been
see.
any.
I see.
If you get me started, I'll talk all day.
No, I'm sure it's a life-defining experience.
Just hoping it's not the only one.
No, sure. No, I mean that in a positive way.
No, and it is. I think science would be a cool next adventure.
It will happen. Sure.
Okay, that sounds good.
I'm intrigued by what these two blobs are, which emission lines they are.
Oh, and can I ask what the cuckoo clock is?
Whenever this green marker for, there we heard it again, whenever it's outside this purple square, it's a warning that the flexure compensation system is not working properly. Now that the green box is inside, until it goes out again, you won't hear the cuckoo clock again.
Okay.
And when it goes outside the box, when this green marker, which is a measure of how much the spectrum is drifting relative to where it should be, drifting, the 2D spectrum is drifting in X and Y. That's what the two coordinates are, X and Y. When this green box is inside, it shouldn't hear that alert, and it should say tracking. When it goes outside, the next time you hear the clock, you'll notice the green point is outside, and this will say seeking rather than tracking, meaning it's not well aligned. It's seeking to align, seeking to track.
This is just pointing the telescope.
This one is not, the corrections it's making is not by pointing the telescope. It's really internal components of the spectrograph. There's something called a tent mirror. It's a grating tilt, and it's the CCD stage, X stage, Y stage. In fact, these are the three things that it can adjust: the grating tilt, the tent mirror, and the dewar. The dewar is the flask that holds the liquid nitrogen containing the CCD. That contains a stage in which the CCDs can move relative to the beam of light. Those are the three controls: coarse and fine control in X and Y. It uses three of those, all three of those things. because when you want to do very fine control, typically you don't have a lot of range. And so what you do is you do the big corrections using the coarse correctors, and then you do the fine corrections with that can make very fine moves.
Like tuning a violin.
Yeah. This kind of system is used in a lot of mechanical systems where you have a coarse dial and a fine dial.
It's probably really complicated, but how is it? What features of the spectrum is it watching to make sure that it's aligned?
Very good question. This is shown in this gray here, up here. You know how I was, let me go back to a different display to explain this. You see these 8 CCDs in which the spectrum is collected. These are called the science CCDs. So the actual science spectrum is, whatever target the telescope is pointed to, its light is being collected on these 8 CCDs. Well, connected to these 8 CCDs, to these science CCDs, one on each side, actually 2 on each side, 2 on each, no, 1 on each side, 1 on each side. Let me see, what does the FCS show? Tell me whether it's 2 or 1 on each side. 1 on each side is a separate CCD, smaller and separate CCD that's bolted onto the right edge, one bolted onto the left edge. Now, so that's one thing this needs. And then where the mask sits, right? So basically light is coming in through the mask, going through the grating, getting dispersed and landing on the CCD. So if something, if there's a star and you're tracking it perfectly, it's going through a slit. But if for some reason, I'll tell you the reason, but if for some reason the light of that star is not landing on the same pixel on the CCD over time, if it's drifting, then you want to correct for that, because the spectrum is otherwise unnecessarily getting blurred out. Now, the thing that can cause it to drift is there's a physical gap between the metal plate through which light is coming. Then it's hitting a collimator mirror, it's going through filters, it's hitting a diffraction grating, ultimately going through a camera, landing on a CCD. There's physical space. The amount of physical space is about the size of this room, actually. I've sat inside DEIMOS, okay? It was being constructed. You were given little tours where you can climb into it. It's like climbing into a space module or something like that, I imagine. Anyway, it's big. It's big because it's going on a big telescope, a 10-meter telescope, everything scales. Now, because of the way Altair's telescopes work, as the telescope tracks the sky, if it were taking an image of a galaxy or a constellation would rotate relative to the detector. So the detector has to rotate in real time. Not only does the telescope need to track, the detector has to rotate. That means the gravity vector is pointed in different directions relative to the components of the spectrograph. So things can bend relative to each other. They can flex under their own weight. That's why flexure compensation system is what this thing is called, this thing that we were looking at here. Flexure, FCS stands for flexure compensation system. For something to flex is for something to bend under its, in this case, under its own weight. So to correct for differential flexure really is what it's correcting for. You don't care if it bends as long as the amount of bending is the same, but that's changing because of the gravity vector changing. So the way it's done again is those CCDs are put on the sides of the science CCD, and next to the mask are 2 fibers on the left and 2 fibers on the right, light fibers. Okay. Now they are like artificial stars that are bolted again onto the cassette that holds the mask. There's a robotic arm that moves different metal plates into that holder. So you can load 11 masks into DEIMOS and select which one you want. Right now, Evan has selected A22BL2. It's a particular metal plate. But the frame in which the mask sits, bolted onto those 2 things, are these 2 light fibers on each side. Now, so they go through the same light path as the light that's, light shining through the slit. So those 2 fibers they're, they are, light is being sent into those fibers. Copper argon emission line lamps are shining into those fibers, but the exit of those fibers makes it look like stars, makes it look like just like another star coming through a slit, real star coming through a slit. These artificial fibers, fiber optic stars. Well, because they're emission lines and because they're point-like emission lines, they produce a series of dots. That's what you're seeing here. The two fibers on the left CCD, two fibers on the right CCD. Left CCD is illuminated by fibers that are on the left side of the mask, right, the right side of the mask. Now, what you want is at the start of the exposure, start of the night actually, when you set your grating tilt and all of that, you take some reference frames like this. You know where the dots should be. In the course of the night, it's constantly taking these. 1 second exposure reads out. Another 1 second exposure reads out. And it does a cross correlation between where the dots should be or where they were when the afternoon calibrations were done and when they are in the course of the night. So it's constantly correcting, and it's correcting using these three things. The grating tilt, if you change the tilt of the grating, it'll move the line in the wavelength direction, move the spot in the wavelength direction. The tent mirror is a mirror that has like a pyramid shape that I believe it can correct an X and Y. And then the doer stage, which is where the CCD sits, can do fine corrections as well. I'm pretty sure the grating tilt does course corrections. I think the tent mirror also does course corrections, and the doer does all the fine corrections in X and Y. I think that's how it's done. But most astronomers, most people who use spectrographs don't know about flexure compensation systems because most spectrographs don't have them. So even astronomers who've done spectroscopy their whole life may not know about flexure compensation systems, but every DEIMOS user does.
Nice.
I'm sorry to interrupt, but I think I'll have to leave now. Something.
No
planned
problem,
may
Pradipta. Thank you for joining, and
Yeah,
we'll have many of
Thanks
these
for such a
sessions.
nice session.
No, you're welcome. You're welcome. There'll be many of these sessions, so feel free to join other later ones as well.
Thank you very much.
Sure. Bye.
So the CCDs are cooled with liquid nitrogen?
Yes.
Okay.
They're actually heated. They're not at liquid nitrogen temperature. They're actually heated. It's ironic. The doer contains liquid nitrogen, but then you heat them above liquid nitrogen temperature, and the advantage of that is then you have better control over their temperature. You can control the amount of heating or not. You keep it at a fixed temp. You want to keep it at a fixed temperature because you want to keep its characteristics unchanged. And so, for example, there have been nights when there's been such severe snowstorms on Maunakea that the crew that goes in to fill liquid nitrogen on a regular basis would not be able to get up to the summit, sometimes for a week. And so then what would happen is the amount of liquid nitrogen in the doer would boil off, and the detectors would start to warm up, and then that's not good for the detectors, etc. So now they have an autofill line where it detects that any doer has low nitrogen, it autofills that. But even that can keep going only for a certain amount of time.
So is it warming up to like room temp? Excuse me. What is the temperature range that we're shooting for the CCDs?
I'm certain here.
Room temperature.
Oh, it says that. Does it say somewhere? Let me see. Where would this be? Let me see if it's. This is a camera specific thing.
It's right there on the left. System overview, CCD temperature is
Oh, yeah.
-115.
That's
Where do you see that?
warm.
The left window, the
This
right
window?
panel.
System
Yes,
overview.
yes, the right
Oh, over
panel.
here. Okay, CCD
Yeah.
temperature -115 in Celsius. Okay. Liquid. What is liquid nitrogen's temperature? -183 Celsius. one of them is minus 196 is liquid nitrogen. One of them minus 183 is liquid oxygen. I think minus 196, which is 77 Kelvin that's what I remember as the boiling point of nitrogen. 77 Kelvin is minus 273 plus 77, so it's minus 196. So it's heated up quite a bit.
But does that not mean that the CCDs are I guess they're in the atmosphere anyway, right? That's
Oh, they're in a vacuum
atmosphere-
chamber. They're in a vacuum
Oh,
chamber.
plus the nitrogen gas, or is that like in a separated system?
Good
They're not.
question.
Excuse me. I'm in the picture in my head was they're just sitting in liquid nitrogen. It's probably not that simple.
No.
Probably a cooling system
It's
of
cooled.
some type. Right.
cooled. Because they're not sitting in any fluid, no.
Right. vacuum.
Because even if it's transparent, that fluid would be sloshing around, would affect the optics of things. So it's not sitting in any optics.
Right.
No, it's not sitting in any liquid. I can hear roosters crowing outside my window. It's getting close to 5. Can you hear them? No, you probably can't because I've got my headset on. Some loud roosters around here. Initially, I looked at the rotate angle of minus 200 from 0.6, and I thought that might be the temperature, and I completely missed the line above it. As you heard yesterday, Evan and I were on this absolutely exquisite island of Molokai on Friday and Saturday. And Sunday morning, we came to the Big Island. It's so beautiful there. Completely unspoiled. Not completely, there are people living there, but so beautiful there. So the cuckoo clock, again, because this green box is outside the window. You see it says seeking up here instead of tracking. The green box is moving further away. It's got a mind of its own. So the cross correlation is not working properly for some reason. There we go. Now it should go from seeking to tracking. There you go, it's tracking. The roosters also stopped crowing. Maybe it's not a real rooster, but an FCS alert. If you see where it says reference images over here, these are the names of the images it's collected earlier to get the reference positions of the dots on the FCS UCDs. Outside range again. I'm going to quickly check in with Evan and I'll be right back. I want to see what's going on, what he thinks is going on with FCS. Be right back, okay? back. Evan seems to be in the middle of a call still, so didn't. Can I stop the live transcript, or is that something we need? Would it take a moment to send out this, to forward your email or Prajita to Deborah and what's their name? Young and Evan. Okay, this is your email, right?
Yeah.
So far it's gone to Liv, Kang, and Jumai, Julian. Okay. I've shared it with Evan already, so I'm only going to share it with Young and Olivia. Sorry, Young and Deborah. Operator, help me write an introduction here, please. Just, it doesn't need to be very long because you've written a very detailed one, good one.
I don't know.
Okay.
Yeah, I have pretty much written everything.
You've written everything, and Young knows the context quite well.
Yes, exactly. Young
Deborah
knows
may
the
not know it
context.
as quite as well.
Yeah.
Okay.
Maybe you should introduce the project to Deborah.
Yeah.
Because I didn't mention anything about the survey or anything.
No,
How
that she
you-
knows. She knows about the M33, M31 surveys, but what she may not know about is emission lines and relics.
Yeah.
I'm going to say as Young knows. Hey, Roy, I'm just writing an email relating to Aprajita's research to some of our collaborators. So pardon us, sorry. Just take care of this one thing. Did I get the slit number correct?
It's 20, right? Yeah,
Slit 20 and A1 and 33P.
that's right.
Is that a reasonable explanation of what we're doing? It's a couple of sentences. Please take a look. Is the font too small? Should I make it bigger?
No, I can read.
Okay.
Yeah, sounds right.
Exposure complete.
Did you find out what's wrong with the FCS?
No, Evan was still on his call. He had his headset on, so I couldn't talk to him.
CCD readout complete.
Okay, I'm sending it off. I added that PS for Deborah just to connect the next email that I'll send her. We're actually past our, I'm going to stop the recording of the Zoom. Let me send this off first. Okay.
ISM is a radio band?
No, ISM stands for interstellar medium.